In November 2024, a routine firmware update reached the smart water meters of Plano, Texas. Within hours, 73,000 transmitters fell silent. The city paid $765,000 to hire 20 field readers, returning a digital grid to clipboards and flashlights. This is not a glitch, it is a structural verdict on the smart grid. Advanced metering infrastructure, or AMI, was sold on 20-year lifespans. Reality has delivered 8% failure rates, billion-dollar repair bills, and a regulator that now mandates automatic compensation. Commodity wrappers around public language models cannot fix this. Critical infrastructure demands sovereign, private, deeply integrated intelligence, deep AI. The failures share a single anatomy. Plano, Toronto, 470,000 transmitters, $5.6 million in initial remediation. Memphis Light, Gas and Water, an 8% failure rate, a $9 million repair fund. Aclara firmware faults reported in Minneapolis, Toronto, and New York City. Inside the device, NAND-flash memory wears silently. The meter keeps reporting numbers, but the numbers are wrong. Software complexity has doubled while testing methods have not. And in the United Kingdom, Ofgem's guaranteed standards of performance now require energy suppliers to pay every customer £40 whenever those standards are missed. Reactive maintenance is no longer cheaper. It is the most expensive option on the table. The deep AI architecture is a 4-layer stack on hardware the utility owns. The first layer is sovereign infrastructure. Private inference engines, VLLM, text generation inference, Bento ML deployed directly onto the utility's Kubernetes clusters or bare metal GPS. The virtual private cloud is configured with strict zero egress rules. The model brain physically cannot phone home. The second layer is RG 2.0, a semantic brain over the utility's own corpus. Technical manuals, historical maintenance reports, firmware source code, all indexed into local vector databases such as Milvus or Qdrant. Retrieval is role-based access control aware. If the operator cannot read a document, neither can the model. The third layer is continued pre-training. Generic llama models do not speak utility nomenclature. Low-rank adaptation, or low-RA, tunes a bespoke model on the enterprise's own legacy codebases. Domain accuracy lifts by up to 15%. The fourth layer is the firmware verification pipeline, and this is the layer that would have caught Plano. Binary targets are identified with EMB and Firmware. Ghidra disassembles the code. A private language model audits the decompiled binary for logic flaws and zero-day vulnerabilities. The candidate firmware is then dropped into a QEMU virtual environment running FreeRTOS, where reinforcement learning agents inside digital twins of homes and substations actively hunt for failure paths. That last step finds vulnerabilities 38% faster than random fuzzing. The numbers underwriting this architecture are not aspirational, they are field measured. Predictive maintenance, when paired with deep models on real telemetry, reduces infrastructure failures by 73%. Maintenance costs fall 18 to 25%. Asset lifespans extend by up to 40%. Unplanned downtime drops 30 to 50. Component lead times shorten by 28%. Safety incidents drop 40%. Behind each of those is a financial fact. Outages cost industrial operators an average of $125,000 per hour. The System Average Interruption Duration Index (SIDI) and the System Average Interruption Frequency Index (SIFI) no longer measure inconvenience. They measure shareholder loss and regulatory exposure. The return on investment calculation collapses to one line. ROI % equals total gain minus total cost divided by total cost times 100. Plug in the Plano numbers: 10.2 million in capital, 765,000 in remediation, an unrecoverable trust deficit, and the case for predictive, sovereign diagnostics writes itself. The boardroom choice is binary: rent intelligence from a public provider or own it. A wrapper sits on someone else's hardware, ships data through someone else's network, depends on someone else's pricing, and offers no defensible intellectual property. A deep AI stack sits inside the utility's own cloud, learns from its own history, respects its own access controls, and becomes a bespoke asset that does not exist anywhere else on Earth. For a sector that powers hospitals, schools, and water systems, the real moat is not the foundational model. It is the domain expertise and sovereign data integration that public API providers cannot replicate. The cost of a dumb meter now exceeds the cost of a smart one. From Plano to Memphis to the UK Ofgem mandate, the lesson is the same. Smart grids need sovereign intelligence. Read the brief, and the next 20 years of resilience starts being engineered.